now finally going to get to integrate fractions. So I'm going to do this version, which is similar to question 5. And over here, I've got your little shopping list, quite cryptic, giving you the kind of the general strategy for solving integrals involving fractions. Now, we didn't need to do this yesterday, but this step 1 is quite common. This question has it. Factor the denominator. So, original question. So I hope we're up to speed on factoring.
I had a quick question about the factoring
Yes.
part. So what would
Yes.
happen if you couldn't factor the denominator?
Well, once you've finished swearing, you'll complain to me because the question is impossible to do.
Okay, because there was a few on WebAssign that were not factorable on the bottom. So I got a little confused. So
there are factoring, and then there is factoring. You can actually do completing the square, which would then involve a use of, but I'm very worried that that was the case because I didn't deliberately put any of those in. Right. But this one factors, would you agree? This would be a normal question, a good one, rather than a weird one. What are the factors then that work for this quadratic? So essentially, two numbers that multiply together give me +8.
-4, -2.
That's the one, right? And that's step 1 done. Now, since this is kind of a template for the questions, I'm going to put in more than I typically would do. And I'm going to put in step 2. Split it into partial fractions using any appropriate method. So this guy here, which I'm just going to rewrite in its factored version. Is going to get split into its partial fractions. I won't bother with the integral dx part right now. You can imagine them being there if you like, but I'm just going to focus on this equals that. Now, we have two techniques for doing this. We saw them yesterday. We didn't really do the general algebraic method much. We did one of them, but we can do, would you agree you can do the cover-up method with this question? Because they're both linear. So I always, me personally, I prefer the cover-up method because of speed. So here goes. This guy here, right? X minus 4, the guy above it, cover up the X minus 4. The value of X that makes that 0 is 4. Plug in 4 to what's left. 4 take away 6 is -2. 4 take away 2 is 2. Oh. So you get -1 for that one. That's fine. Okay, let's get B now. This fella. X minus 2. Cover up X minus 2. What do you put in here to make it 0? You put in 2 to make it 0. And you get -4 on the top and -2 on the bottom. And that comes out as what? +2. Let me double check that in case I screwed up. Cover that up, put in 4, 2 in the bottom. Okay, 2 in the bottom and -2 in the top. That works. Check this one again, plug in 2, -4 in the bottom, -2. Yep, we got it. Are you comfortable about the partial fractions and how I got the numerators? Right. So if you want to, you can now stick in the integrals. They're just a distraction to me, so that's why I didn't write them down. Well, that's step 2 done. Step 3. Integrate each one separately. Now, in this case and in this case, if you remember my little list yesterday, aren't these just logs, both of them? This one is -1, the natural log of x take away 4. And this one is 2 times the natural log of x minus 2. Are you happy about the integral of this gives me a log, and the integral of this gives me a log. So anything like 5 over x plus 1, -2 over x minus 3, anything that has that shape to it will be a log when you find its antiderivative. So that's step 3. Step 4, add a plus c or evaluate the integral using the limits integration. In this question here, would you agree it's an indefinite integral? So there's step 4. If this question had been the integral from 5 to 6, then all I would do in step 4 then would be you find the natural log of x minus 4 plus 2 times the natural log of x minus 2, and you evaluate it from x equals 5 to x equals 6. So that's what I mean about evaluate the integral using the limits integration. So in this case, what would we get? Negative the natural log of 6 take away 2 plus 2 times the natural log of 6 take away 2. That's the first chunk. Subtract negative 5 take away 4 plus natural log of 5 take away 2. Natural log of 4. One of these two is not right. There we go. Natural log of 2. 2 times the natural log of 4. Take away is add, so you're going to add the natural log of 1. This guy's 3, so you're going to take 2 natural log of 3. So what do I have? I have negative the natural log of 2, 2 log 4s, take away 2 log 3s. So if you have limits of integration, right, if you have numbers here, it does mean that step 4 does require a fair amount of work, right? You have to calculate some things. But it's just basically plug in the big number, take away, plug in the little number, and subtract them, right? The usual way. Now, some things can happen. If you plug in the number and the number ends up being -3, because it can happen sometimes. Technically speaking, you should never have a negative in the log. But don't we have that little make it positive trick that allows us to use it? So just in case you're doing a calculation that is involving putting in values of x that may be negative, you know, here, just remember that you can just turn them into positive because of that trick. Are we comfortable with how to do this particular question and the 4 steps that were involved in it? Any questions about the first one we've done now? Okay. Next one. This is like question 7. It's going to be 4y squared, take away 7y, take away 12. And on the bottom, it's a y plus 2, a y take away 3, dy. Do I need to do step 1 in this question? Not really a trick question, it's a silly question, isn't it? Why didn't you factor it? It's already factored. So I'm going to jump right into step 2. So these 3 guys, you agree that they're all linear. So I can use my cover-up method, right? The short, quick way of doing it. Okay. I need a piece of paper. Here we go. Let's just hide those guys because they don't need to be here right now. Let's figure out who A is. Y on the bottom. You cover up Y. What number do I put in for Y now?
0.
0. So on the top, what, -12? On the bottom, -6. -12 on the top, -6 on the bottom. Final answer, +2. You check it, 0, 0, -12. 0 add 2 is 2, 0 take away 3 is -3. 2 lots of -3 are -6, -12 on top, -6 on the bottom, +2 is the answer. Okay, let's look at the next one. I want B. Cover up that guy. Would you agree that the number I have to use now is -2? Right, now I'm going to do this in my head, and this is scary. So if you get a different answer, tell me. -2 on the top. 4 lots of -2 squared. Take away 7 lots of -2. Take away 12. Ooh, that's going to be good. That's going to be 4. That's going to be 16. Add 14. Take away 12. I make the top 18. Okay. Plug in -2 here, you get -5. Plug it in here, you get -2. -5 times -2 gets me +10. I make that 9/5. Do you agree with me?
8/5.
8/5. Okay, let me check it. So do you get 16 here?
Oh, I can't see your paper. It's not over far enough.
Oh,
Oh, yeah. That's the reason why I couldn't see it. I was looking at the
Okay.
16.
not a problem. Ah! 9/5. Y +2 is still in the bottom. Okay, time for the last guy, C. You're going to plug in 3 here. Okay, so it's going to be 4 lots of 3 squared, take away 7 lots of 3, take away 12. That's going to go in the top. And if you plug in 3 in the bottom, you're going to get 3 times 5 in the bottom. So there's going to be a 15 in the bottom. That's 9, that's 36, take away 21, take away 12, that's 33, that's 3, 3 out of 15. I make that positive 1/5. Any disagreements about any of those 3 top numbers? Right. Now, do you know that I'm writing these in a rather ugly format, but that's okay. It's actually helpful to leave them that way. So if you want to integrate these guys, this guy is 2 natural log of y's. This guy is 9/5. The natural log of y add 2. And this guy is 1/5. The natural log of y minus 2 add c. And that is a downright ugly answer, and it's also correct. So are you happy about this guy becomes these partial fractions, and these partial fractions integrate basically as logs, multiples of logs.
Just a quick question.
Yeah.
I think you changed the denominator to y minus 2 instead of y minus 3.
You think, oh, here?
No, the one to the right.
Oh, here. Good, but that's an easy fix. Thank you.
Quick announcement, it just started snowing.
Contradictory announcement. It ain't snowing at all here. But it will. Do you think I've just got a little bubble of heat above my house?
Maybe. It's only very, very lightly snowing at my place.
Yeah. It'll come. I know it will. Okay, I think I've done enough examples of linear on the bottom. Are we good with these, or do you need another one? Your chance, you know, you're the boss. If you feel you want one more, just say it, because I bet you're not the only one. If you
One
feel
more.
happy, one more it is. Okay, let's put one with an extra bit of work on it then. Let's put in a question that needs a step one. Would you agree that the denominator, oops, I'll rewrite that question again. Would you agree that the denominator needs to be factored? Right, which is step one. Okay, let's do it. What can I do to x cubed minus 4x as far as factoring goes?
Pull out an X.
Okay, good start. Can you do anything with x squared minus 4? Because I can. Can you do it? Do you recognize x squared minus 4? Because it does factor.
X plus 2, x minus 2.
Does anybody know what it's called, this particular situation? That's a fancy name. It's called a...
Difference of squares.
There you go. Or a difference of two squares back and home. Right. Now it's ready. By that, I mean it is 3 linear terms that we should, hopefully, turn into partial fractions and then integrate. And I'm doing my usual ignore the integral symbols until later. Okay, you tell me, what is A? See if you can do it in your head. Use the cover-up method. What is A?
-1/4.
I agree. Okay, somebody else is getting the next one. What number or fraction is B? Any takers? Can't hear you if you're saying something, Bessida.
Is it -5/8?
Let's find out she's right. X plus 2, right? That's the one that's going to go here. Right, that's the one I'm looking for, B. Won't you plug -2 into what's left? On the top, you're going to get what? -2 squared, add 1. On the bottom, you're going to get -2 times that guy. 5 on the top, -2 times -4 is -8. And I get -5/8. You agree?
Wouldn't the bottom be positive?
Positive, yeah.
Oh! Do you agree now? Okay. Last one. What's C going to be? Well, I'll do this a bit quicker. You got C, you cover that up. Don't you put 2, right? The value of x makes that 0. So 2 on the top. 2 squared plus 1 is 5. 2 times 4 is 8. Oh, 5/8 again. That's interesting. So we got what? A -1/4, a 5/8, and another 5/8. So I can now integrate. negative 1/4 the natural log of x, 5/8 the natural log of x add 2, and 5/8 the natural log of x minus 2. Plus c, because this one's indefinite. In step 4, you just add the plus c. We feel comfortable about how to do integrals of fractions using the partial fraction technique. Now, these are going to be the easiest ones that we do today. And as long as the terms are linear, that means these guys in the bottom are all x's, 2x plus 1s, whatever it might be. This method makes it really fast. We're now going to look at questions where this method does not work, where we have to use the general algebraic method. So this is an example of this is question 9. Okay. Now, it's going to split as an a over x minus 1. Remember what we did yesterday, what goes above x squared plus b?
bx plus c.
Okay, so if there's an x squared plus 4, an x squared plus 7, something like that, you're going to look at bx plus c. Now, the general algebraic method, and I'm going to just rewrite this again for my benefit, you don't need to, is much longer and much more detailed, right? There's a lot more to do. So you write these guys, and then what you do is that you combine them back together again. So in this case, you need an x squared plus 4 top and bottom. So that's essentially multiplying by a special version of 1 so that the denominator has these two guys. What am I going to multiply the second fraction by? This fraction gets multiplied by x squared plus 4 top and bottom, but what will this fraction get multiplied by?
X minus 1.
Right. Have you noticed that each fraction gets whatever the other guy's got? Right. Now, that makes the top row, when you combine them together, a really, really big, awkward-looking numerator over this guy. And over here, you've got the original. And then what we do is we say, look, we know algebraically that these are identical, right? They're equal to each other. And since the bottoms are the same, that logically means that the tops are the same. And what very often happens is that once you've done enough of these, can't you ignore that line and go, or sorry, can't you ignore this middle line and go from that line to this line? Can you imagine? You do this and then you immediately write that. Saves you one line of working if you can handle it. Now the tricky part, this is going to be what we call the general algebraic method. This is what I'm doing right now. I think it's called the general because it's used all the time. It can be used everywhere, right? You can generally use it anywhere you want. It's all about choosing x's. And the reason why it kind of works is that this expression is equal to 5 for every single value of x in the universe, right? It has to be equal to every single time. So if we choose our x's wisely, we will be able to find A, B, or C, and eventually we'll find all of them. The trick is choosing a good x value, and even harder than that, choosing when to use it. So what would be the best choice right now?
I would choose 1.
I like your thinking. Can you explain what your brain was telling you to choose that? Because it's the right answer.
Well, so that the B would be 0, basically. That term would be 0, and then you can solve for A.
Agreed. Do you see, by choosing x equals 1, you essentially destroy this. It becomes 0. And that means you've only got one missing variable. Your goal is to only have one missing letter each time. So choosing x equals 1 is perfect choice. So what do I have? I have 5 on this side. I have A. I have 1 squared plus 4. And can I just say plus 0 to save a whole lot of writing? Because that's what you're going to get anyway, isn't it? Which means A times 5. And because WebAssign is really, really nice, A equals 1. If I had made this question up, A would have been 17/43, right? It would have still been correct. It just would have been really ugly fractions. Now, I'm not going to guarantee that every single WebAssign question is going to have nice A, B, and C, right? So don't be worried if you get 17/5 or -3/9 or 3/19 or something. That can happen quite easily, actually. Now, once you know what somebody is, you go back here and you rewrite them. But with A turned into, in this case, 1. Now, since A is 1, isn't it just one lot of x squared plus 4? Right? Then we repeat the process. There is a good number this time. Who should you choose for x? Any number in the universe is allowed, apart from number 1, because we've used that one up. Evan, I think you were going to say something. I interrupted you.
I said 2, but I was just thinking about it.
And you're not so sure now.
No, I would definitely try out a 2. Yeah.
So you try 2. If you tried a 2, you would end up with B's and C's. So you wouldn't have one variable. So that's why I wouldn't choose 2. If you plug 2, both of these live. I think someone said it, but I didn't quite catch it.
Could you try 0?
Yes. Now, why is 0 going to work? Well, let's see. 5 is equal to 0 squared plus 4 plus, B times 0 means the B's disappear, plus C, and a 0 take away 1. So what have I got? I got 5 is equal to, that doesn't matter, 4. C times -1 is negative C. Subtract 4 from both sides. And now you've got C. Now, if you'd chosen any other number except 0, you would have been left with things like 4B plus C is 10. 2B plus C is 47, right? You'd be left with a B and a C. You always look for a value of x that makes it so only one letter lives, right? Only one variable survives the process. Now, once you know, as we do, that C is -1, you go to the last one you wrote down and replace the C, that's this guy here, with -1. So now I have x squared plus 4 plus bx take away 1, x minus 1. And now we can do the last x that you need to pick, right? So you've had to choose 1 to get A. You didn't have any choice, really. You had to choose 0 to get C. Again, there was no real choice. But once you've only got one letter left, in this case, isn't the one guy that we don't know is B, your life becomes really easy. What value of x should you choose in the last question?
1.
Good choice. Any other? Totally correct. 1 is good. Any other number?
10.
Yep. Any other number? Ten works, by the way. The only number in the world that I won't choose is 0, because wouldn't 0 kill the bee? So the answer for who do you choose as your last value of x, right? The last one, you get the missing letter. And the answer there should be anything you like as long as you don't kill b. And I like 1 because I like small numbers, right? Could I have done 10? Sure. Could I have done 42? Sure. Would I get the same answer? Guaranteed. So it don't matter. That sounds amazing, doesn't it? That you could pick any value of x you like and the b you get's the same number every single time.
But if you were to choose 1, wouldn't that make the x?
Oh, darn it. You're right. I told you can't make it 0, and I just chose one that makes it 0. So let's fix this problem. I can't pick 1 then. Who shall I pick? Be lazy. What should you pick?
2?
2.
Yeah, just move up the scale, get it. I would have found that out in 10 seconds. Wouldn't I have found it out when I plugged it in? Oh God, it's disappeared on me. So pick anything you like as long as it doesn't make the b disappear. So what do we get? We get 5, 2 squared plus 4 plus x times 2 is basically 2b, take away 1 times 1. So that's 5. 4 add 4. 2b, take away 1. 8 take away 1. Was 8 take away 1? 7. Subtract 7 from both sides. Yay. We now have everybody. And did you notice how darn long this question took? Can you see why I avoid the general algebraic method whenever possible? It just it won't be that you won't get the answer. You got the right answer. There are questions you can't avoid it. If there's a square in it somewhere in the denominator, you can't avoid it. You're stuck with this method, right? You just got to live with it, right? So, okay, I'll live with it. So I'm going to rewrite all of this information now that we know it. The original question was to integrate that guy. We've discovered that it's a, which is 1 over x minus 1, plus b, which ends up being negative bx, negative x, plus c, which ends up being negative 1. So that's b and c over x squared plus 4. And we got that one. So I should be able to integrate this. 1 over this guy. Check. See these two guys? Separate them out. So integrate each fraction separately. That's what I'm doing here. Step 1 and 2 hammed up here, right? So you take each piece separately. Now there's good news in here and there's bad news in here. You would think, oh, thank goodness we're done. Well, let's see. This guy, yep, no problems with that. I did show you yesterday an extension of the inverse tan. Can you remember the extension when it wasn't x squared plus 1, but x squared plus 4 or 9? The 4 gives you a half and an inverse tan of x over 2. Okay, minus that guy. Well, that's the awkward part. The middle fraction is x over x squared plus 4. I need to integrate x over x squared plus 4. How am I going to do it? How am I going to integrate that guy?
U sub
Yeah. Who's the u sub going to be?
x squared plus 4.
That makes sense? U sub, denominator, x squared plus 4. So just when you thought you'd finished the question, darn it, you've got an extra bit of work to do. Well, if you differentiate with respect to x, you get this guy. You do the crossover. Oops. You do the crossover, you get that. And then you isolate the dx. So I'm going to have the integral of x over u times 1 over 2x du. They cancel. And essentially, I get 1/2 of u. You're happy about this half being written that way rather than 1 over 2u because it looks ugly. If you don't, are you happy with that version, which is the same thing? Right. So you get 1/2 natural log of u, which becomes 1/2 the natural log of x squared plus 4. And now you can say, thank goodness, it's finished. That was a very, very long question. But any question that has an x squared plus 1 or x squared plus 4, like this question, that's how it's going to get done, right? So at least once you've seen one, you've seen them all, right? Because the only thing that's going to change are the numbers. Right? You're going to do the same process. Anything about question 9 you want me to talk about?
Can you just explain super briefly how we got 1/2 arctangent x over 2 really fast?
Oh, this here? Yeah.
Because I know that
Right, there's a guy that's called this, which is a standard integral that you just memorize it, right?
yes.
Right. There is an adaptation to this where you have an a squared, right? Like a 4 or a 9 or a 16. And it's 1 over a, the inverse tan of x over a. And it's just basically a formula for getting the answer to integrals that look like this. So when you tell me I have an x squared plus 4, for instance, I look at that and say, oh, you mean 2 squared? If, however, it was 1 over x squared plus 25, the change would be 5 squared. So basically, you just know that. Standard integrals.
Okay, thank you.
Are we good? Any other questions? Okay, we got time for a third possibility. This time I'm going to do a version of 8. And this one has a square in it as well. But this time the square is an x plus 1 squared. So x minus 7 squared in brackets, x plus 22 squared. Anything that has this in it, this is how you're going to tackle that one. So let's do the partial fraction part. It's going to be split into 3 distinct fractions. The most common mistake is people think you only need 2, which is those 2. But actually you need this one and this one, right? So the square term generates 2 separate partial fractions, and it needs them both, right? Trust me, I'm a mathematician, right? You need them, right? It has to be that way. Now, in the general algebraic method, shouldn't I now take these guys and put them back together again? And don't write this down, because I've just realized I never gave myself enough room. Each of these fractions is going to be converted into a fraction that has this common denominator. And the way that we change each of these fractions is by multiplying them by a special version of 1. So I'll look at the guy at the end. See this x plus 2 guy? Would you agree that, I'll put it in red, would you agree that these guys are missing an x squared plus 1 term? Okay, the middle one has got an x squared plus 1. So what's this middle term missing? This one here.
X plus 2.
So that's the special version of this one. Now, the hardest one you probably get is the last one. Isn't it missing an x plus 1 and an x plus 2? It's missing 2 pieces. So this one gets an x plus 1, x plus 2 guy. Are you happy about how you split it into 3 pieces and what you need to do to put them back together as a single fraction? Now, as a single fraction, then you're going to have a x plus 1, x plus 2 added to b, just an x plus 2, added to c is going to be an x squared plus 1. Technically all over this, and it's going to equal x squared plus x plus 1, technically all over this. But if I skip that line, can I just say the top line's equal? Saves me having to write a whole load. Because all I'd need to do is a line over this, and then the next line would look like that. Are we okay up to this point, where the pieces that I've got came from?
Just a quick question for the last part for C, multiplied by x squared plus 1. I might have missed that, but shouldn't that be x plus 1 squared?
Yes, thank you. That's very important. Shouldn't that be x plus 1 squared? Yes, it should be. Right, now, I like this because I like things that you have to think about. I need to choose a value of x. I need to choose a very special value of x. One that's going to make everybody else, that's the A's, B's, or C's, any 2 of the 3 disappear and leave me with just one guy behind. And there's only one value of x that is going to help me out here.
-2.
And if you choose -2, doesn't it kill that guy and that guy? You agree? -2 makes this 0, makes that 0. So that means nothing plus nothing plus c times -2 add 1 squared. And on this side, if you choose -2, you get what? -2 squared. Put it in here. -2 squared plus a -2 add a 1. So let's see what we get here. That's -1 squared. That's c. 4 take away 2 is 2 equals 3. And I have now got my first guy. Everything here, every x here, gets replaced by -2. So that's 4 take away 2, add 1, which gives me 3. Disappears to 0, disappears by 0. 1 squared is still 1, so C gets me that. And now I know a little bit more than I did before. I now have x squared plus x plus 1. It's still a times this guy plus b times this guy plus c, which is 3 times this guy squared. Okay, guys, time to choose an x. Can't choose -2. That's been done. Who are you going to choose?
-1.
I like -1. Why are you picking -1? Because it does work.
It cancels out the last part and then A.
Essentially, it kills these two, doesn't it? I mean, there is a logic to the x's, isn't there? There's certain x's are going to do stuff and other x's are useless. So if you plug -1 in here, you get -1 squared plus -1 plus 1. If you plug in -1 here, you basically get a 0. You plug -1 in here, you get that. And if you plug -1 in here, you get another 0. So that, take away that, this is 1. That's 1 times b. That's why they get paid the big bucks. Doesn't b just equal 1? So what do I now know? Well, I now have x squared plus x plus 1. It's a times this guy plus b times this, which is basically just that, plus c times this. Last x. You agree? Anything will work as long as it doesn't kill A. Would you agree? Any value of x will work as long as it doesn't kill A. So give me any value of x that will work in this last one.
0.
What a good choice. You read my mind. Why do you think I was going to pick 0 as well? Because Jessica picked it. Why did I pick 0 rather than 42 or something ridiculous like that?
It's easy.
Yeah, nothing else. Would you agree most of the time I'm less likely to screw up if I'm calculating with a 0 in it than if I try to do it with some ridiculous number like 42. So I'm going for it. 0 squared plus 0 plus 1. A times 0 plus 1, 0 plus 2. X plus 2 just turns into what? 0 plus 2. This fella turns into 3 lots of 0 plus 1 squared. So that's 1, 2a, that's worth 2, and that's worth 3. So 2a plus 5, subtract 5 from both sides, and a is -2, which means that we are pretty close to the finish. The original question, which was this one, has now been split into its partial fractions. It's an a -2 over x add 1. It's then got a b, which is 1 over x plus 1 squared. And then a c, which is 3 over x plus 2 dx. And I'm going to split them into 3 separate pieces. Okay, this guy is -2, -2, the natural log x plus 1. This guy at the end is 3 lots of the natural log of x plus 2. They're going to be a c here. There's always one bad boy. I need to integrate 1 over x plus 1 squared. Any suggestions about how to integrate 1 over x plus 1 squared? Because once that's done, this question is dead. Evan?
U sub.
U sub of x plus 1 would work. Any other way? That's not normally that works perfectly fine. Any other way of doing it? Okay, well, assume that you did it by U sub, you get -1 over x plus 1 when you're finished.